gentlemen, class recording has started. So, chapter 9 starts off with Newton's law of universal gravity. And we kind of discussed yesterday that up until, actually a lot longer than Newton, but we had, that is not what I wanted to do. Sorry, buddy. There we go. No, I'm good. That up until, or for a long time, we had this view of gravity. That Galileo kind of said, hey, I know you can tell me that the thing that makes this object fall to the ground is gravity, but what is gravity? And our answer was, we don't really know what gravity is. But Newton comes around, and at the very least, sets some ground rules for gravity with his law of universal gravitation. And, like it says here, the force of gravity between any two objects with masses m1 and m2 separated by distance r is attractive and has a magnitude of F given by. And we talked about this formula yesterday. So first, gravity is an attractive force. It pulls things together. It is incorrect to say that gravity pulls things to the ground. Sorry, it's not incorrect. It's not inclusive enough, right? It's an attractive force. It pulls things together. But the idea that Newton realizes about gravity is that it is not something specific to us here on Earth. While that is all of our experience, well, not at this point, up in Newton's time, our only experience with gravity is the gravity here on Earth. Newton realizes, and like I said, based on the commercial that we saw earlier, right? Allegedly, the apple falls from the tree, and Newton realizes that the apple falling from the tree and the moon in orbit around the Earth are exactly the same thing. A little different application, but it's the same idea. And Newton realizes that gravity is not something specific to us here on Earth, that it is a universal thing that exists between any two objects with mass, not just the Earth and objects here. So, how much gravity there is between any two objects with mass depends on a couple of factors. First, it depends on the mass of the two objects. So that's the m1 and the m2 part. It also depends on how far apart they are. But then the other factor that gets thrown in here is that capital G. And yesterday we introduced that as the universal gravitation constant. And its value is given to you right here. The one thing that we talked about yesterday is that it has a factor of 10 to the minus 11th power built into it. And that leads us to the realization that gravity is actually a very weak force. Okay? I jumped ahead a little bit, but it relates to what we're doing. Okay? Any time that we calculate the force of gravity between two objects, this factor, the universal gravitational constant, which when it's not written out in scientific notation, looks like that, that factor is built into it. So gravity is actually a very weak force. It only becomes significant when we're talking about the area surrounding very large objects, objects that have a lot of mass. So we experience gravity as a significant effect on our lives only because we're very close to a significant mass, that being the Earth. All right? If you think about it, other kinds of forces are much stronger than gravity itself. If you've ever done one of the party trick, if you have a balloon and you rub balloon on your hair, right? If you have hair, you need hair to do this. If you rub balloon on your hair, you can stick it to the ceiling, or stick it to the wall, or something like that, right? You've seen this done before? Yes, no, okay. You've never seen that done before? Try it next time, next party. If you ever have parties, I mean, I don't want to. Yeah, you can invite. She's available for parties apparently. They don't even really have to be significant parties. Just call her up. So. What? I mean, so I had to verify. So anyway, if you think about the situation where you can rub a balloon on your hair and you can stick it to the ceiling, the electrostatic forces that exist between the balloon and the ceiling are stronger than the entire force of gravity of the Earth pulling down on that balloon, because it sticks up to the ceiling, right? So gravity is actually a very weak force because it has that value built into it, right? But because we're so close to a big object, we feel it more significantly. Okay? The other thing that we talked about yesterday was that while we think of gravity as something that pulls objects down to the ground, gravity, following Newton's third law, can't exist on its own. It needs a pair to go with it. So if gravity from the Earth pulls the ball downward, action-reaction says, if gravity from the Earth pulls the ball down, gravity from the ball pulls Earth upward, right? That whole action-reaction idea. Now, just because they feel the same force doesn't mean that the same thing happens to them, right? We also talked about the effect that mass plays into this. That this object, right, the lacrosse ball, it has a small mass, so its acceleration is much bigger than the acceleration of the Earth that has a very large mass, right? They feel the same force, but that doesn't mean they behave the same way. We have to throw mass into that discussion as well. Okay? Good there. Okay. The other thing that we talked about yesterday is this idea, right? Did we get to this graph yesterday? Yeah. Okay. Like the title says, gravity decreases rapidly with distance. Looking at the formula for the force of gravity that exists between two objects, right? We said it depends on a couple of things. The mass of the two objects and the distance between them. The distance between them is where in the fraction? It's in the denominator, right? Meaning that there is what kind of relationship between force and distance? Let's go first with what? It's an inverse relationship, right? Because distance is on the bottom, force is here. Distance gets bigger, force gets smaller. But the important idea being that not only is it an inverse relationship, mathematically, we are squaring the distance. So we refer to this as an inverse square force law. That's pretty inventive with the name that they came up there. They called it inverse square because it's inverse and it's being squared. So it's, you know, somebody worked hard on that. That's all I'm saying. Came up with that name. So. But like it says here, key point. The force of gravity decreases as the inverse of the square of the distance. So, as we move objects farther apart, the force of gravity between them decreases. And that's true. But, with that squared factor, if we move two objects twice as far apart, it's not 4 times, it's 1/4, because it's 1 over r squared, right? So it's the same idea as like kinetic energy, right? But now the squared part is on the bottom, right? So if we move something 10 times as far, it's 1/100th of the 1/100th of the force. But we also talked about that because of the mathematical relationship, not because of the mathematical relationship, the mathematical relationship shows us, right? Missy, we also talked about the idea that mathematically, what kind of relationship are we looking at? It's an asymptote. It's an asymptotic relationship. Meaning that even though, as we get farther and farther and farther, right, as r gets bigger on the x-axis, f gets smaller and smaller and smaller. That's the inverse part. But it will never hit 0. The only way that we could make f in this equation be 0 would be if r was infinity. And you can't have infinity meters. That doesn't, Right? It can be really, 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 really big, but it's got to be a number. It can't be infinity, right? So as we get farther and farther apart, that force of gravity gets smaller and smaller and smaller, but regardless of how far away they are, there is always at least some force of gravity between them. Okay? Good there. All right. Real quick, let's just see how the formula works. Quick example 9.1, it says, a girl takes her dog for a walk on a sunny beach as shown below. Find the force of gravity between the 45 kilogram girl and her 11 kilogram dog when they are separated by a distance of 1 meter. Right? There's Newton's law of universal gravity. We start plugging in things we know. We know that the mass of the girl is 45 kilograms. We know the mass of her dog is 11 kilograms. We know that they are 1 meter apart. But then the one factor that is included in every one of these calculations is this G factor, the universal gravitation constant. Because it is a constant value, it never changes, regardless of what the two objects are that we're trying to calculate the force of gravity between. So now we have all the things that we need to calculate this force of gravity. We just have to plug it in. I would suggest, it hasn't come up very much yet in this class, but I would suggest that you use the scientific notation button on your calculator. If you don't know how to use that scientific notation button, at the very least, use parentheses to try and keep this number together, because if you don't, sometimes your calculator gets lost in order of operations and may give you the wrong answer.
And what's the value?
Well, let's talk about that. So, 3.3 times 10 to the minus 8th. First, are we okay with that? Okay. Second, what are we calculating here? The force of gravity. So what unit should it have on it? Okay. It's still a force. It should have newtons. If we look at the value for the universal gravitation constant, this is the unit that goes along with it. It's a big crazy unit that has lots of parts into it. But in the end, they all have to cancel and leave us with newtons because we're calculating a force. So as long as your distances are in meters and your masses are in kilograms, that will happen. Good there. Okay. All right, as far as today goes, let's talk about the next idea. Gravity is a force. It is a vector quantity. While the gravity between you and the Earth, or the gravity between the Earth and this ball, is much stronger than the gravity between me and this ball, or you and this ball, or whatever it might be, if we want to look at the total effect of gravity, we have to look at the vector sum. Right? We've given the vector sum a couple of fancy names before, right? We could also call the vector sum the what? Well, that's mathematically it would be the hypotenuse of a triangle, right? But generally, we could call it the what? What do we call the vector sum? We give it a fancy name. It's the resultant vector, right? Now in this case, because we're dealing with the resultant vector of force, right, we can also call it the what? If we're dealing with the resultant of many forces,
Oh, the sum of the force.
the sum of the forces, or the
Net force.
net force, right? When we're talking about the effect of gravity, right, we can add up the forces just like we can add up any other forces. Yes, they're gravitational forces. Usually we've only put one gravity force in a problem, but it still follows the same rules. Okay? For example, each of the three equally spaced and equally massive objects shown below experiences gravitational forces due to the other two objects. Rank the objects in order of increasing magnitude of the total gravitational force they experience. Indicate ties where appropriate. So, which one of these three feels the most force? Which one of these three feels the least gravitational force? 1 minute, talk to the person next to you. Go. What? Greater than, less than? What did we look in fourth grade? The alligator eats the bigger number,
You know, I know it's less than.
or the Native American shoots the smaller number.
I never heard that.
Never heard that one before?
I just memorized them.
Well, back in my day, we said the Indian shot. So I changed it to the Native American. You know, so.
Wait. So yeah. So well, why does B have less? I thought B would have more. Yeah, no. So if you would put it pulled on by A,
Like A and B is louder, but then A has two.
All right, so let's discuss. Okay.
Yeah, let's
So, where is B? In the middle. A pulls on it. Which way? Let's go with directions. Because nobody watching the video is going to understand that way. Right? So, B, A pulls on B. Which direction? To the left. C pulls on B. Which way? To the right. What is the vector sum of two forces that pull on something to the left and the right? 0. The net force on B is 0. Okay. As we discussed, B pulls on A to the left. But if if A pulls on B to the left, Newton's third law says A also has to feel a force this way. Okay? Equal and opposite. Nope. B pulls on A to the right. If A pulls on B to the left. Remember, it's an attractive force, right?
I just don't like drawing it that way.
Sorry. A also experiences a force from C. Any two objects experience gravitational force between them. It doesn't matter if something is in between them, they'll still feel that force. Okay? I feel a force from you, but I also feel a force from Rachel if you go, she's behind you, right? Those are two separate forces. But B's force is greater than C's force. Why? Closer. Okay? Technically, how much less force does C have on A than B has? 1/4, because it's twice as far away. All right, does that make sense? Okay. But C is also feeling forces, one from B, one from A. How much? Well, how much are they compared to these two arrows that I've drawn? Exactly the same, but in the other direction. But this object is just asking about the magnitude. So A and C experience exactly the same force, but in different directions.
Wait a second. If C's pulling B that way, when B's
C is pulling B to the right.
right, so B's pulling and C's to the left. So then the only one acting on it is B. Only one acting on A is technically B because
No.
A and C cancel out.
C. No, because C is also getting acted on by A.
But it's going in opposite directions, so they cancel out too.
But those are on two different objects, right? Blues are acting on A, reds are acting on C. They can't cancel each other out.
No, I know, but I'm just saying, like, technically the only one pulling A, like, if there was a value for it, it would be B.
Nope.
Because B
C is also.
But C's not, it's going to the left, like, if B's, it's going to the right.
If we removed B out of this picture, C would still be pulling A.
Okay.
There are two forces pulling on A, one from B and one from C.
Because it's going to the right.
Yep. And there are two forces pulling on C, one from B and one from A. And they would both be there whether the other one was there or not.
So the one now always going to be less than, on the other
Ooh. How about this one? Okay. So right below this one, you have, or right below the example we just did, you have this example here. Same thing. Discuss. 1 minute. Go. We're not asking you about acceleration.
Oh, so yeah, it's just, I'm so lost.
I thought you said that gravity, like, it would feel the same, like, force or gravity on, like, two objects. Like, what if the mass isn't, like,
I thought you told me this one. Then I said I'll do that later.
That may have been what you heard, but that's not what I told you.
yeah, like, I copied it down. Gravity's force is the same on two objects, no matter the mass. But the acceleration is different on the two objects because of the mass. Does that make sense?
I'll tell you.
I'm
Wait,
so
are you saying
confused.
A has the least amount?
I'm not saying anything right now. I'm just writing stuff up on the board.
It's saying it's going three that way, three forces. Three forces, the other two are pulling it that way. So B's going to pull that way, that way, that way. And it's saying pull four that way. So. So C has a third. Yeah, so C would have a third. Same with B, A, C. Yeah.
All right. So let's discuss. Okay. All right. I made up some numbers just to kind of illustrate real quick what we're doing. Okay. So we said that that's how we calculate the force between two objects, gravitational force between two objects, yes?
Yeah.
Okay. First, I just kind of disregarded G for this discussion because it would be included in all of the calculations. They would all go up by or down by that amount. So let's forget about G right now. Okay? Then, just to make my life easier, I said that M is going to be equal to 1. Okay? 1 kilogram. And also to make my life easier, I said that distance R is also going to be 1. And that means that's 1 as well. Okay? Everyone got the ground rules so far? Okay. I started with B. B, the mass of number 1, that would be A, so I just plugged in 1 for that. And then the mass of B is 2, right? Oh, sorry, messed up. My bad. I may have screwed up this whole thing, but that's okay. The answer is not going to be different because I screwed it up the same way the whole time, but no, that was right. Okay. Those are the two forces, one from A, one from C. Everyone see where I got that from? Yes, no, maybe. All right, let's talk about A. A feels a force from B, right? It's not 3. It's actually 2. Okay? Those two are the action-reaction pair. This is B pulling on A. This is A pulling on B. Yes? Okay. This would be 2 over 4. Okay, 1/2, yes. But I want to do the 2 over 4 to kind of make sure that we understand this, right? In this case, this is A, 1. This is C, 2. But the distance now is how far? Twice as far, but we have to square it. That's where the 2 over 4 comes from. Good there?
So does that mean that the 2 is coming from B, like action reaction?
No. The 2 is from the masses, right? This is the mass of A. This is the mass of C.
No, I'm saying the first 2.
Oh, the 2 comes
Yeah.
from B.
Yeah.
Yeah. Okay. But remember, if A feels this much force to the right, C has to feel that much force to the left. Yes? Those are action-reaction pairs. Okay? B and C, right? The mass of each one is 2. So 2 times 2 on the top. But the distance between them is only 1, right? So 4. Action-reaction pairs, right? So now, if we add them up, right? The total force that A feels is 2.5 to the right. The total force that B feels, 2 to the right. The total force that C feels, 4.5 to the left. So the correct ranking here is C is greater than A is greater than B. Sorry, yeah, but I mean, if they're, C is still greater than A, sorry, that's decreasing, I guess, but, All right, good there? Got it. Rachel, We didn't get to the example that you need to do 61 and 60, or whatever those last two ones, but it gets into more mathy stuff. So, all right. Hey, if you didn't do the homework last night, except for the last two problems, it's pretty conceptual. You might want to take a look at it. The answers are posted. Tomorrow, we'll start in on packet 9.2, dealing with the applications of gravity, and we'll go from there.